In this module, we're talking about Dalton's law of partial pressures of gases. So Dalton's law is a pretty simple concept. It says that if you have a mixture of gases, that the total pressure in that container is equal to the sum of the partial pressures of the individual gases. What does that mean? Well, first of all, what does partial pressure mean? So if we had this container and it had two gases in it, the partial pressure of the blue gas, whatever that is, would be the pressure that that gas would have in that same container at that same temperature if it were in there by itself, like this. So the partial pressure of the red gas would be the same thing. The pressure that this red gas would exert in the same container at the same temperature if it were in there by itself. So if we have this is the partial pressure of what's called gas A for the blue one, and this is the partial pressure of gas B. The total pressure is just equal to the sum of the partial pressures. Partial pressure of A plus partial pressure of B is equal to the total pressure. If there's more than two gases, then just add them all up, the partial pressures. That's Dalton's law of partial pressures. Now, one situation where this comes up a lot in chemistry is when a gas is collected over water. If you see those words, or if the situation is such that it's collected over water, then you'll use Dalton's law of partial pressures. Here's how. So first of all, what does it mean to be collected over water? Well, imagine you have a closed jar container here, and there's a reaction occurring in an aqueous solution, and one of the products is a gas. And let's say that gas, there's a glass tube in here with a rubber tubing connected to it, and a bigger jar in the middle that has two pieces of glass tubing through the top of it, one connected to the reaction vessel, and one connected to a longer piece of glass tubing that goes over to a beaker. So when this reaction over here occurs, the gas comes out here, goes through here, exerts a pressure on the top of the liquid. The liquid goes where there's less resistance, which is up this glass tube, through the rubber tubing, and is collected over here. And we do several experiments like this. But let's say one of the things that we want to know is what the pressure of the gas is inside of this container after everything's finished. Well, you can't measure the pressure of the gas by itself because there's water here, and whenever there's water present, some of those molecules of water will escape from the surface and become a gas. So there are molecules of water, gas, mixed in with the molecules of the gas from the reaction. You can't separate them. This is a situation where Dalton's law of partial pressures comes in. In this situation here, the pressure inside here is going to be equal to the atmospheric pressure. And you can measure that by looking at a barometer. So let's say you look at a barometer, find the atmospheric pressure. What we really want to find, though, for the calculations that we normally do with this kind of experiment, is we want to find the pressure of the gas by itself. But what we measure is the atmospheric pressure, which is equal to what's called the vapor pressure of the water, plus the partial pressure of the gas in itself. So what we do is we rearrange this equation a little bit and solve for the partial pressure of the gas. It's just the atmospheric pressure minus the vapor pressure of water. Now, we can look that up. There are tables of this. It depends upon the temperature. The higher the temperature, the higher the vapor pressure of water. But you measure the temperature here, go in a table and look up the vapor pressure of the water, subtract it from what you measured on the barometer, and the difference is the partial pressure of the gas, which you normally need to know. So for example, this table right here is a table of the vapor pressure of water as a function of temperature. So temperature, 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 and the vapor pressure in torr of water. Now, let's say you measure the atmospheric pressure and it's 29.78 inches of mercury, and the temperature is 24 Celsius. What would the pressure of the gas in that, so this is the experiment we're just looking at, the partial pressure of the gas in that container. What would it be? Well, because these are in torr, we're going to have to convert our atmospheric pressure into torr. To do that, all you do is convert inches to millimeters. Now remember, there's 2.54 centimeters per inch, which is the same as 25.4 millimeters per inch. And this is an exact conversion. And also, 760 torr is the same as 760 millimeters of mercury, which is also exact. So this number right here is the only one with limiting sig figs, 4 sig figs. Anyway, do the math, and it ends up the atmospheric pressure is about 756.4 torr. To find the vapor pressure of the gas by itself, we just look up the vapor pressure of water at this temperature. So we come over here 22.38 torr is the vapor pressure of water at that temperature. Subtract it from the atmospheric pressure, and the difference is 734 torr. And if we needed it in atmospheres, we just take this, multiply it by 1 atmosphere per 760 torr, and we'd end up with 0.9658 atmospheres.